Welcome to Astro Odyssey. Explore the universe. The transition begins with a deceptive stillness. On the surface of Earth, we are accustomed to the heavy, comforting blanket of the atmosphere, thick, nitrogen-oxygen soup that scatters blue light and softens the harsh reality of the void. But as the ascent begins, the physics of our existence undergo a violent transformation. The sky does not simply darken. It bruises, turning from azure to a deep royal indigo, and finally to a black so total it feels tactile. This is the first psychological hurdle of the infinite. The realization that the sky is not a ceiling, but a thin, fragile veil. As the last molecules of air slip away, the stars undergo a chilling metamorphosis. No longer do they twinkle, a charming effect caused by atmospheric turbulence. Instead, they become piercing, unwavering needles of light, burning with a ferocity that suggests they are watching the voyagers with a cold, nuclear indifference. Leaving the pale blue is less an act of travel and more an act of birth. Behind us, Earth remains a vibrant marble of swirling white clouds and deep cobalt oceans. But from the threshold of the exosphere, it looks terrifyingly lonely. The mechanical ballet mentioned by the early pioneers becomes apparent as we enter low Earth orbit. Every satellite, every fragment of debris, the moon itself, are locked in a complex gravitational choreography, dictated by the curvature of space-time. We are no longer walking on a floor. We are falling around a sphere at 17,000 miles per hour. This is the true beginning of the voyage, the moment the human mind must expand to accommodate a three-dimensional reality where up and down are replaced by inward and outward relative to the solar well. The first major milestone. Is the moon our silent silver companion? Up close, the poetic man in the moon dissolves into a scarred, monochromatic wasteland of basaltic plains and impact craters. It is a graveyard of solar system history, its lack of atmosphere preserving every footprint and every meteor strike for eons. To pass the moon is to leave the last outpost of the familiar. Beyond it, the distances begin to stretch. The space between worlds is not empty in the way we understand emptiness. It is a sea of invisible forces, solar winds, magnetic filaments, and the constant, streaming radiation of a middle-aged G-type star we call the Sun. As we push toward the rusted plains of Mars, the Sun begins to shrink, losing its status as a majestic disk and becoming a blindingly bright point of light. Mars represents the limit of human familiarity, a world of extinct volcanoes like Olympus Mons and canyons that could swallow the United States whole. But Mars is merely the gateway to the outer kingdom. Crossing the asteroid belt, we move from the terrestrial to the celestial. The transition to the realm of the gas giants is a transition of scale. Jupiter looms not as a planet, but as a system unto itself, swirling, turbulent king of hydrogen and helium. Its great red spot, a storm larger than our entire homeworld, has raged for centuries, a reminder that on this scale, the lifespans of empires are but a few frames in a cosmic film. Jupiter serves as the great protector, its massive gravitational well acting as a vacuum cleaner for the inner solar system, intercepting comets and asteroids that might otherwise find Earth. But as we drift past its moon, Europa, with its hidden subsurface oceans, we are drawn further into the cold. Saturn's rings trillions of ice particles shimmering in the dim, Sunlight for a brief moment of aesthetic grace before the descent into the true dark. Beyond Uranus and Neptune, the sun is no more than the brightest star in the sky. We enter the Kuiper Belt, a crowded neighborhood of icy dwarfs and frozen remnants. And finally, the Oort Cloud. Here, at the very edge of the sun's gravitational influence, the silence is absolute. We are at the shoreline of the interstellar ocean, looking out into a void where the distance to the next star is measured not in miles, but in years of light-speed travel. The crossing of the heliopause, the boundary, where the sun's solar wind finally surrenders to the pressure of the interstellar medium, marks the true beginning of the abyss. Behind us, the sun has shriveled into a brilliant, yet solitary point of light. No longer providing warmth, only a distant golden memory. Ahead lies the great silence. This is the interstellar medium, a realm often mischaracterized as a total vacuum. In reality, it is a thin gas of hydrogen and helium atoms, interspersed with microscopic dust grains from long-dead stars. As we move deeper into this darkness, the scale of human time begins to feel like an evolutionary blink. In the abyss, distance is so vast that light itself, the fastest messenger in the universe, takes years to traverse the gaps between neighbors. To travel here is to realize that space is not just a place, but a fabric of time. When we look ahead at our destination, Alpha Centauri, we are not seeing it as it is, but as it was 4 years ago. We are traveling through a living museum of the past. The psychological weight of the abyss is the first true challenge for the cosmic voyager. On Earth, we are defined by boundaries, horizons, coastlines, and borders. In the interstellar deep, there are no landmarks. There is only the fixed grid of stars, which, despite our incredible velocity, appear motionless, like diamonds embedded in a ceiling of infinite height. The vacuum outside is absolute. It is a cold that reaches toward absolute zero, where molecular motion nearly ceases. Yet, within this void, there is a strange, haunting beauty. We pass through nebula vast, towering clouds of gas and dust that act as stellar nurseries. Up close, these are not the vibrant, glowing tapestries seen in telescope photos, but ghostly, translucent wisps that stretch for trillions of miles. They are the cathedrals of the cosmos, where gravity is slowly, patiently sculpting the next generation of suns and worlds. As we approach the Alpha Centauri system, the duality of the universe reveals itself. We find not one sun, but a complex gravitational dance of three. Rigil Centaurus and Ptolemy, two stars similar to our own sun, orbit one another in a graceful millivodal loop, while the dim, red spark of Proxima Centauri clings to the periphery. This is our first lesson in cosmic diversity. The solo nature of our own solar system is an outlier. Most stars in the galaxy are part of families, binaries, triplets, and clusters. We witness the birth of planets in the habitable zones of these stars, fire-forged rocks and icebound moons that may or may not harbor the chemical precursors of life. But even here, in the closest neighboring system, we are merely on the front porch of the Milky Way. The journey continues deeper into the galactic disk. We are moving toward the Orion Arm, a spiral of stars and gas that houses our corner of the galaxy. The density of stars begins to increase, and the darkness of the abyss is replaced by a crowded, glowing field of stellar diversity. We see blue supergiants, massive stars that burn with a fierce ultraviolet intensity. living fast and dying young in spectacular supernova explosions. These explosions are the ultimate alchemy of the universe. In the heart of a dying star, under unimaginable pressure, the heavy elements gold, iron, and the carbon in our own DNA are forged and scattered into the void. We are made of this star stuff, and as we travel through the remnants of these ancient explosions, we are essentially retracing our own chemical ancestry. Beyond the stars lies the dark matter mystery. As we observe the rotation of the galaxy, we realize that what we see, the glowing stars and shimmering nebulae, only a fraction of the story. There is a hidden scaffolding, a gravitational glue that holds the galaxy together. It's invisible to our sensors, but felt in the way every star moves. The abyss is not empty. It is a complex web of dark matter and dark energy, forces that we are only beginning to name, let alone understand. We are passengers on a vessel of logic and light, sailing through a sea of mysteries that challenge the very foundations of our physics. The journey through the abyss is a journey of humility, reminding us that for every answer we find in the light, the darkness holds 1,000 more questions. Leaving the Orion Arm behind, we set our sights on the galactic center, a place of density and violence that defies terrestrial imagination. As we move inward, the stars crowd together until the night sky is no longer black, but a permanent, shimmering twilight of millions of suns. The gravity here is a tangible force, a chaotic tug-of-war between stellar giants. At the very center lies Sagittarius A*, the supermassive black hole that acts as the anchor for the entire Milky Way. It is a point of no return, a place where the laws of physics as we know them break down. Time slows to a crawl near the event horizon, and light is bent into distorted rings of fire. This is the engine of the galaxy, a dark heart around which all life and light revolve. But even the Milky Way, with its hundreds of billions of stars, is but a single cell in a much larger organism. We break free from the galactic disk, rising above the plane of the Milky Way until we see it in its full majestic spiral, glorious swirling whirlpool of light suspended in the intergalactic void. Ahead of us lies the local group, a collection of galaxies including the Great Andromeda Spiral. The distances here are no longer measured in light years, but in millions of light years. The void between galaxies is even more profound than the interstellar abyss. It is a place of such extreme emptiness that a single atom might be the only inhabitant of a cubic meter of space. Yet even here, there is movement. Galaxies are rushing toward one another, drawn by gravity, destined to merge and form even larger structures in a process that takes billions of years. The departure from our solar heliosphere is not a sudden leap, but a slow drowning in the vastness of the Milky Way. As the sun's influence wanes, we find ourselves immersed in the interstellar mediumism. To the untrained eye, the space between stars is a vacuum, but to the eyes of physics, it is a turbulent sea. We are now drifting through the body of a titan. The Milky Way is a disk 100,000 light-years across, a spinning record of matter where every node is a star and every groove is a spiral arm. We move toward the Orion Arm, our local neighborhood where the density of matter begins to rise. Here we encounter the Orion Nebula, a colossal cloud of hydrogen and silicates that serves as a stellar nursery. This is not a static cloud. It is a violent, churning factory. Inside the nebula, we witness the pillars of creation on a grand scale. These are towers of cold, molecular hydrogen, light years tall, acting as the incubators of the cosmos. Gravity is the master sculptor here. Within these dark, dense knots of gas, the pressure mounts until the core of a protostar reaches the critical flashpoint of nuclear fusion. We see the first light of a newborn sun piercing through its dusty shroud, creating Herbacaro objects, jets of ionized gas shooting out from the poles of the young star like cosmic blowtorches. These jets carve out hollow cathedrals of light within the dust, illuminating the nebula from within in shades of crimson, violet, and gold. This is the violent beauty of creation. For every star that is born, a shock wave ripples outward, compressing more gas and triggering a chain reaction of life across the arm of the galaxy. The narrative of the galaxy is also one of recycling. We witness the supernova remnants, the tattered, glowing veils of stars that have already met their end. When a massive star dies, it doesn't just vanish. It exhales its heavy elements iron, gold, and carbon into the surrounding space. These elements are the seeds for future planets and, eventually, the chemical basis for life. We are sailing through a graveyard that is simultaneously a garden. The shock waves from these distant explosions act as the heartbeat of the galaxy, rhythmically pushing and pulling on the gas clouds, ensuring that the cycle of stellar birth and death continues for billions of years. As we rise above the plane of the Milky Way, we leave the forest of our own stars and look out into the metagalaxy. The diversity of galactic forms is a testament to the chaotic history of the universe. We see majestic spirals like the Pinwheel Galaxy, their arms tightly wound with blue hot stars and dark dust lanes. But then we encounter the giants, the ellipticals. M87, a monster sitting at the heart of the Virgo cluster, is a featureless golden swarm of trillions of stars. Unlike the Milky Way, it has long since used up its gas. It is a red and dead galaxy, a retirement home for the oldest suns in existence, the most haunting chapters of the cosmic story are written in the shapes of irregular galaxies. These are the survivors of cosmic trauma. We observe galaxies that have been cannibalized by larger neighbors, their stars stretched out into long, glowing tidal tails. This brings us to the most profound realization of galactic life. Galaxies are not islands. They are predators and prey. We look toward Andromeda, our nearest large neighbor, and realize it is rushing toward us at 250,000 miles per hour in 4 billion years. The Milky Way and Andromeda will begin their great merger. To a human observer on a planet during this time, the sky would be a terrifying and beautiful sight. However, the collision is a misnomer. Because the distance between individual stars is so vast, galaxies pass through each other like ghosts. It is unlikely that even two single stars will physically collide. Instead, it is a gravitational dance. The two spirals will swing around each other, stripping away stars and flinging them into the intergalactic void like sparks from a fire. Over hundreds of millions of years, the distinct spiral shapes will dissolve, and the two empires will settle into a single massive elliptical galaxy Milkomata. This is the ultimate fate of the local group, a slow-motion transformation from chaos into a singular, eternal empire of light. Asterisk. Beyond the clusters of galaxies lies the greatest mystery of all, the void. As we move out of our local group Enter space is so empty that the concept of distance becomes almost meaningless. Between the great walls of galaxies lie boats, voids, expanses of nothingness, millions of light years wide. If you were placed in the center of such a void, you would see no stars, no galaxies. Only a darkness so absolute it feels like the end of the universe. Yet, when we look at the universe on its largest possible scale, a pattern emerges. Galaxies are not scattered randomly. They are strung along invisible filaments of dark matter, forming the cosmic web. These filaments meet at massive junctions, where superclusters of thousands of galaxies huddle together. We are seeing the skeleton of the universe, the scaffolding upon which all light is hung. This structure is the echo of the Big Bang itself, quantum fluctuations from the dawn of time that have been stretched by billions of years of cosmic expansion into the web we see today. As we leave the suburban quiet of the Orion Arm and plunge toward the galactic center, the density of stars becomes overwhelming. In the core of the Milky Way, stars are packed so tightly mere light weeks apart that the night sky on a hypothetical planet would be bright enough to read by. But at the dead center of this celestial swarm lies an invisible throne. This is Sagittarius A*, a supermassive black hole containing the mass of 4 million suns compressed into a point of zero volume. To approach it is to witness the ultimate distortion of reality. We see stars like S orbiting this invisible point at terrifying speeds, whipped around by a gravitational force that defies human intuition. Here, space is not a static background. It is a fabric being twisted and stretched like taffy. Surrounding the event horizon, the point of no, returns the accretion disk. This is a swirling maelstrom of gas, dust, and stellar debris, accelerated to a significant fraction of the speed of light. Friction and magnetic forces heat this material to billions of degrees, causing it to glow with a fierce, white-hot intensity. This is the great irony of the cosmos. The blackest objects in the universe are often the brightest. When a black hole feeds voraciously, it becomes an active galactic nucleus, AGN, or a quasar. These cosmic lighthouses emit more energy in a second than our sun will in its entire 10 billion year lifespan. They are so bright they can be seen from the very edge of the observable universe, acting as beacons that tell us where the first galaxies formed in the dark of the early cosmos. However, black holes are far more than just cosmic vacuum cleaners. They are the ultimate regulators of galactic evolution. As the accretion disk spins, it generates immense magnetic fields that funnel charged particles into relativistic jets. These beams of plasma shoot out from the poles of the black hole at nearly the speed of light, extending tens of thousands of light years into the intergalactic void. This is the feedback loop of a galaxy. By blasting this radiation outward, the black hole heats up the surrounding clouds of cold hydrogen gas. Because stars require cold gas to collapse and ignite, the black hole effectively acts as a thermostat. If it feeds too much, it gets too hot, and star formation shuts down, the galaxy becomes quenched and red. If the black hole is quiet, the gas cools, and a new generation of stars is born. The very existence of our sun may be due to this delicate balance maintained by a monster millions of light years away. Even as we master the mechanics of the black hole, larger mystery pulls at us. We look beyond the borders of the Milky Way and realize that our entire galaxy, along with Andromeda and dozens of others, is being dragged. We are part of the Laniakea supercluster, a vast, heavenly watershed of galaxies. At the heart of this structure lies the Great Attractor, a gravitational anomaly equivalent to tens of thousands of Milky Ways. The Great Attractor remains partially shrouded by the zone of avoidance, the thick, dusty plain of our own galaxy that blocks our view of the deep universe. It is as if we are trying to look through a fogged window at a giant moving in the distance. This mysterious force reminds us that the visible universe is merely a thin layer of foam on a deep, dark ocean. We are moving toward a destination we cannot see, driven by a physics we are only beginning to name. Asterisk, the deeper we venture, the more we realize that everything we have seen, the stars, the gas, the black holes, accounts for only 5% of the universe's total composition. The rest belongs to the dark sector. Dark matter acts as the invisible glue, providing the extra gravity needed to hold galaxies together. Without it, the Milky Way would fly apart like a broken carousel. And then there is dark energy, mysterious pressure that is currently pushing the very fabric of space apart at an accelerating rate. We are witnessing a cosmic tug-of-war. Gravity tries to pull the universe together into monsters like the Great Attractor, while dark energy tries to rip it into an eternal, lonely void. Asterisk, our journey now takes a turn that defies the linear passage of time. To understand the monsters in the dark, we must travel backward, past the birth of the first stars, to the moment the universe was a screaming, incandescent point of infinite density. As we look further into the distance, we are looking further into the past. The light from the most distant galaxies has taken over 13 billion years to reach us. We are now entering the epoch of reionization, a time when the universe was a dark, opaque fog of neutral hydrogen. There were no stars, no planets, and no black holes. It was the cosmic dark ages. Suddenly the darkness breaks. We witnessed the first light, the birth of population 3 stars. These were the primordial giants, hundreds of times more massive than our sun. Born from the pure hydrogen and helium left over from the Big Bang, they lived fast and died with a violence that shook the foundations of space. Collapsing into the very first black holes, these seeds would eventually grow into the supermassive monsters, like Sagittarius A** that we encountered in the galactic centers. As these first stars ignited, their intense ultraviolet radiation stripped the electrons from the surrounding hydrogen gas, clearing the fog and making the universe transparent for the first time. This was the moment the cosmos truly opened its eyes. But we can go even further back. Beyond the first stars, we hit a wall of fire, the cosmic microwave background, CMB. This is the oldest light in the universe. It's a snapshot of the cosmos when it was only 380,000 years old. At this stage, the universe was so hot that it was a plasma-thick, glowing soup of protons and electrons. Light could not travel through it. It was constantly being bounced around like a ball in a crowded room as the universe expanded and cooled. A moment occurred called recombination. Electrons and protons finally joined to form the first atoms, and light was suddenly set free. That first flash is still traveling through space today, stretched by the expansion of the universe into low-energy microwaves. It is the afterglow of creation, a map of the tiny ripples in density that would eventually become the Great Attractor, the Milky Way, and the ground beneath your feet. To reach the depth required for this script, we must pause at the very edge of the Big Bang singularity. Here, the language of mathematics begins to fail. We are in the realm of quantum gravity, where the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single superforce. We explore the concept of inflation, a fraction of a trillionth of a second where the universe expanded faster than the speed of light. This isn't just a historical footnote. Inflation explains why the universe looks the same in every direction. It smoothed out the wrinkles of space-time, leaving behind the seeds of the cosmic web we see today. If the universe had expanded just a fraction slower, it would have collapsed back on itself long ago. If it had expanded faster, matter would never have been able to clump together to form galaxies. We are living in a universe that is fine-tuned to a degree that borders on the miraculous *2. The first second is to understand the DNA of reality. As we travel back past the cosmic microwave background, we move into a regime of heat and density that defies the imagination. At 1 microsecond after the Big Bang, the universe was not filled with stars or atoms, but with a quark-gluon plasma. This was a perfect fluid, a roiling ocean of elementary particles where the temperature was so high, trillions of degrees, that even protons and electrons could not hold together. Here, we witness the strong nuclear force in its rawest form, battling the immense expansion of space to bind quarks into the first stable building blocks of matter. Within this first second, a cosmic war was fought that determined the very possibility of our existence. The baryogenesis. For every particle of matter created in the furnace of the Big Bang, an equal amount of antimatter should have been produced. In a perfectly symmetrical universe, these two would have instantly annihilated each other, leaving behind a universe filled with nothing but pure, sterile light. Yet, as we peer into the quantum haze, we observe a broken symmetry. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. This tiny, infinitesimal imbalance is the reason the stars, the Earth, and your own body exist today. We are the leftovers of a cosmic massacre, survivors of a near-perfect cancellation. As we push even closer to time zero, we reach the electroweak epoch. Here, the universe undergoes a series of phase transitions, similar to water freezing into ice. But on a fundamental level, we witness the moment the Higgs field turned on. Before this moment, particles had no mass. They zipped through the vacuum at the speed of light, ethereal and weightless. But as the universe cooled, the Higgs field condensed, acting like a cosmic molasses that gave particles their substance. Simultaneously, the forces of nature began to split apart. Imagine a single, primordial superforce. As the temperature dropped, gravity was the first to break away, becoming its own distinct entity. Then came the strong force, followed by the weak and electromagnetic forces. This spontaneous symmetry breaking is the ultimate origin of the laws of physics. We are watching the rulebook of the universe being written in real time, dictated by the cooling of the vacuum. As we accelerate our perspective beyond the local superclusters, the familiar shapes of individual galaxies begin to blur. We are no longer looking at places, but at a structure. This is the cosmic web, the largest coherent pattern in nature. From this distance, galaxies appear like tiny dewdrops, clinging to an invisible spider web of dark matter. These filaments, stretching across billions of light years, are the highways of the universe. Along these threads, gas and matter flow into massive junctions called nodes, where gravity is so concentrated that thousands of galaxies huddle together in a frenzy of light. Asterisk, but to understand the web, we must look at what it surrounds, the voids. We drift into the Boat's void, a region of space so vast and empty that it defies human comprehension. It is a sphere of nothingness, 330 million light-years in diameter. If the Milky Way were in the center of the Boat's void, we would not have known. Other galaxies existed until the 1960s. This nothingness is not truly empty. It is a realm where the density of matter is so low that a single atom might wander for 1,000,000 years without ever striking another. The voids are the negative space of creation, the bubbles of dark energy that are pushing the filaments apart, stretching the web to its breaking point. Asterisk, within this web we encounter the Great Wall, a colossal filament of galaxies that stands as a testament to the power of gravity over eons. It is here we realize that we are part of something called Laniakea, Hawaiian word for immeasurable heaven. What is a galactic watershed? Just as water flows down a mountain into a valley, galaxies within Laniakea are sliding along gravitational currents toward the Great Attractor. This movement is the heartbeat of the universe, a slow-motion migration of billions of suns toward an invisible center of mass. But even this grand movement is being challenged. Dark energy, the mysterious pressure of space itself, is acting as a cosmic wedge, forcing these superclusters apart faster than gravity can pull them together. We are witnessing the beginning of the Great Divorce. Asterisk. We now push our journey into the far future, moving through time as easily as we moved through space. We witness the Stelliferous Era, the age of stars, coming to a close. One by one, the great blue giants explode. The yellow suns, like our own, swell into red giants and then shrink into white dwarfs. The universe begins to redden. Eventually, only the red dwarfs remain teeny, frugal stars that sip their hydrogen like a fine wine, lasting for trillions of years. But even they must fade. We enter the degenerate era. The universe becomes a graveyard of zombie stars. White dwarfs cool into black dwarfs, cold spheres of carbon and oxygen that no longer glow. Neutron stars and black holes become the only landmarks in an increasingly dark ocean. During this time, the sky as we know it disappears. Because space is expanding so rapidly, other galaxies are pushed beyond our cosmic horizon. If a civilization were to rise during this era, they would look up and see a sky of total, impenetrable blackness, unaware that other galaxies ever existed. Asterisk, in the unimaginable distance of the future. 10 raised to power 40 years from now, even matter itself begins to fail. If protons are unstable, the very atoms that make up the remnants of planets and stars will simply dissolve. The universe becomes a realm of black holes. For eons, these monsters will be the only things left, prowling the darkness and occasionally merging in a final, violent shudder of gravitational waves. But even black holes are not eternal. According to the laws of quantum mechanics, they slowly leak energy through Hawking radiation. A black hole with the mass of our sun would take 10 rests to power 67 years to evaporate. The supermassive monsters at the center of galaxies will take 10 rests to power 100 years. In their final moments, these titans will vanish in a tiny, brilliant flash of gamma rays. After the last black hole evaporates, the universe enters its final stage. Asterisk, we arrive at the heat death. This is not a death by fire, but by cold. It is the state of maximum entropy. The universe has expanded so much that the temperature is uniform everywhere, just a fraction of a degree above absolute zero. There is no more energy to be traded, no more work to be done, and no more information to be recorded. Time, for all practical purposes, ceases to have meaning because nothing ever happens. The universe becomes a vast, cold vacuum of stray photons and neutrinos, drifting forever in a void that has forgotten the light of the stars. Asterisk, we pull our perspective back, retreating from the cold end of time, back through the filaments of the web, past the great attractor, through the spiral arms of the Milky Way, and down onto the surface of a small rocky planet orbiting a stable, middle-aged star. We realize that the monsters in the dark and the quantum foam are not separate from us. The calcium in our bones was forged in the hearts of those dying stars we witnessed. The iron in our blood was scattered by the supernova that carved the Orion Nebula. The very hydrogen in the water we drink is a direct remnant of the Big Bang's first 3 minutes. We are not merely observers of the universe. We are a part of it that has developed eyes and a mind. We are the stardust that has begun to ask questions. In the face of the infinite silence of the heat death, our brief moment of existence becomes more precious, not less. We are the universe's way of experiencing its own majesty. For a few short decades, we have the privilege of standing on this pale blue dot, looking up at the velvet black, realizing that we are home. Asterisk, the narrative of the cosmos is often told through the lens of cold physics, but the most profound chapter is written in our own biology. We begin this deep dive by tracing the lineage of a single atom of iron in your blood. That atom was not born on Earth. It was forged in the blinding white core of a star 20 times more massive than our sun billions of years ago. In the final seconds of that star's life, it underwent a nucleosynthetic frenzy, fusing silicon into iron, because iron is the most stable element. The star could no longer produce energy to support its own weight. In a fraction of a second, the star collapsed and rebounded in a Type II supernova. This explosion was the ultimate act of biological delivery. It scattered that iron across the interstellar medium, where it eventually drifted into a cold cloud of gas that would become our solar system. When you breathe, you are engaging in a chemical exchange powered by the debris of an ancient cosmic cataclysm. We explore the heavy element enrichment of the galaxy, the metallicity of space. Without the death of the first generation of stars, the universe would have remained a sterile desert of hydrogen and helium. There would be no rocky planets, no carbon-based molecules, and no observers to witness the beauty. Our existence is a direct consequence of stellar mortality. We live because stars died. We further examine the late heavy bombardment, a period where comets, icy messengers from the outer solar system slammed into the young Earth. These were not just destructive impacts. They were the delivery trucks of life. These comets carried amino acids and water, the essential solvents and building blocks of the first cells. We are quite literally a cocktail of cosmic leftovers, stirred by gravity and sparked by the energy of a Geat-type star. Asterisk, as we look deeper into the why of our existence, we encounter the anthropic principle. This is the realization that the fundamental constants of physics seem to be dialed in to allow for complexity. We explore the strong nuclear force. If this force were just $2% stronger, protons would be stable, and stars would have burned through their fuel in minutes. If it were $2% weaker, the universe would consist of nothing but hydrogen. No chemistry, no life. We dive into the cosmological constant, the value of the energy density of the vacuum. If this number were slightly larger, the universe would have expanded so fast that galaxies could never have formed. The cosmic web would have been ripped apart before the first thread was spun. If it were slightly smaller, the universe would have collapsed back into a singularity. Within seconds of the Big Bang, we are living in a Goldilocks universe, a reality that exists on a mathematical knife edge. This leads to the profound question of information theory. Is the universe a giant computer? Is the script of reality written in the language of mathematics? We examine the holographic principle, the theory that all the information in a 3D volume like our universe can be described as being encoded on a 2D surface at its boundary. This challenges our perception of solidity. We are not just matter. We are data, organized by the laws of physics into a coherent, self-aware narrative. Asterisk, finally. We zoom out beyond the observable universe. Our telescopes can only see 46 billion light-years in any direction. The distance light has traveled since the Big Bang. But the universe is likely much larger, perhaps infinite. This brings us to the multiverse theory. According to eternal inflation, our Big Bang was not a unique event. Instead, it was like a single bubble forming in a vast, ever-expanding ocean of inflationary space. In this view, there are countless other bubbles, other universes, each with its own laws of physics, its own constants, and its own history. In some, gravity might be a repulsive force. In others, time might run backward or have multiple dimensions. We explore string theory. It's the idea that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings of energy. These strings vibrate in 11 dimensions, most of which are curled up so small we cannot see them. This suggests that our cosmic web is just one brain membrane. It's floating in a higher dimensional space called the bulk. When two of these brains collide, it may trigger a new Big Bang, an eternal cycle of death and rebirth that transcends our single timeline. Asterisk. Our journey through the cosmic web is not merely a tour of gas and dust. It is a search for home. As we move from the macro scale of galaxies down to the micro scale of star systems, we encounter the exoplanet revolution. For most of human history, we believed our solar system was the blueprint for the universe. We were wrong. The cosmos is a gallery of the bizarre. We begin with 55 Concrete E, a world twice the size of Earth, where the pressure is so immense and the carbon content so high that the planet's interior is likely composed of solid diamond. Here, the geology is a literal treasure map, but the surface is a hellscape of molten lava. We move to HD 189733b, a cobalt blue gas giant that looks serene from a distance, but possesses a terrifying secret. It rains glass sideways, in winds that howl at 7 times the speed of sound. These worlds challenge our definition of habitability. We explore the eyeball planets tidally locked to red dwarf stars, worlds where one side is a permanent frozen wasteland and the other a perpetual sun-scorched desert. Only in the thin Terminator line, the ring of eternal twilight, could liquid water and life potentially cling to existence. This leads us to the shadow biospheres. Could life exist in the methane lakes of worlds like Titan, or in the subsurface oceans of Enceladus, powered not by sunlight, but by the tidal friction of a giant planet? We are forced to consider non-carbon life beings based on silicon or ammonia, breathing gases that would be lethal to us, living in environments that resemble our deepest nightmares. The catalog of planets is a testament to the fact that if a law of physics allows a world to exist, the universe will eventually build it. Asterisk, if life is a common occurrence in the cosmic web, then we must look toward its ultimate evolution. We introduce the Kardashev scale, a method of measuring a civilization's level of technological advancement based on the amount of energy it can harness. Type 1. A civilization that can harness all the energy of its home planet Earth is currently at approximately 0.7. Type 2. A civilization capable of capturing the entire energy output of its host star. Here we witness the construction of a Dyson sphere, a megastructure of orbiting solar collectors that encloses a sun, capturing every photon to power planet-sized supercomputers. Type 3. A galactic civilization that controls the energy of an entire galaxy. As we observe these hypothetical galactic empires, we see them engaged in stellar stewardship. A Type 3 civilization wouldn't just inhabit planets. They would move stars, harvesting hydrogen from gas giants to extend the life of their suns. But they face an ultimate enemy, the expansion of space. As dark energy pushes galaxies apart, even a Type 3 civilization finds its borders shrinking. We explore the final project of a super civilization, the attempt to survive the heat, death. They might build computational hubs around evaporating black holes, utilizing the slow leak of Hawking radiation to power a digital existence for trillions of years. Or, in a final act of defiance, they might attempt to create a baby universe in a laboratory, triggering a controlled Big Bang to escape our dying bubble and start the cycle of life anew in a fresh pocket of the multiverse. Asterisk. We conclude this movement by returning to the human heart. How do we reconcile our 3-pound brains with a universe that is 93 billion light-years wide? We explore the concept of cosmic pessimism, the idea that in the face of such vastness, human suffering, joy, and history are mathematically zero. But then, we pivot to cosmic wonder. The very fact that the universe is intelligible is a miracle. As the physicist Freeman Dyson once said, "The more I examine the universe and the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. We are the eyes of the cosmic web. Without you saw some form of conscious observer, universe would simply be a dark room with no one to see it. We provide the meaning to the mathematics. Our insignificance is not a burden. it is a liberation. It means that we are free to create our own purpose, whether we are a lonely accident or a common occurrence. We are the only part of the universe that can look at a black hole and describe its beauty, or look at the end of time and feel a sense of awe rather than just cold calculations. Asterisk, we move beyond human history, beyond the life of the Earth, and into the long dark of the cosmos. 10,000 years from now, the Earth's Milankovitch cycles suggest a new ice age. But human-induced warming has altered the rhythm. The stars in our night sky begin to shift as the sun moves through the local interstellar cloud. 50,000 years from now, the Voyager 1 and 2 probes, currently silent husks, will pass near other star systems. They are the first fossils of our species. 0.5 million years from now, the constellation Orion will be unrecognizable. The red supergiant star Betelgeuse has long since gone supernova, leaving a glowing nebula in its wake. 1 billion years from now, the sun's luminosity has increased by 10%. The Earth's oceans evaporate. The pale blue dot becomes a scorched, monochromatic desert. The era of complex life on Earth ends. 0.4 billion years from now. The Milky Way and Andromeda begin their first gravitational brush. The sky is filled with a chaotic swirl of billions of new stars. 100 trillion years from now, the Stelliferous era ends. The last red dwarf star exhausts its fuel and fades into a black dwarf. The universe goes dark. 10 rest to power. 40 years from now, the degenerate era concludes. If proton decay is real, the very atoms of the dead stars dissolve into radiation. The only solid objects left are black holes. 0.10 rest to power. 100 years from now, the last supermassive black hole evaporates via Hawking radiation. The universe reaches a state of absolute maximum entropy. This is the heat death. The clock of the universe effectively stops. Asterisk, if the universe is a machine for creating complexity, then life is its ultimate product. We move from the timeline of death to the diversity of living things. The lithovers of rogue planets, on planets ejected from their star systems. Life survives in the core's heat. These are silicon-based organisms that eat rock and move at the speed of shifting tectonic plates. To them, a million years is a single afternoon. The gas bag aviators of Jovian worlds. In the high-pressure atmospheres of gas giants, we find creatures the size of cities living hot air, balloons that filter feed on atmospheric chemicals and communicate through low-frequency radio waves, the crystalline thinkers of pulsar moons. On moons bathed in the intense magnetic fields of pulsars, life has evolved as magnetic alignments within crystal lattice. They are solid-state beings, thinking with the speed of light, perceiving the universe through electromagnetic fluctuations rather than sight, the extremophiles of the voids, in the boat's void. Solitary star readers drift between galaxies. They are vast, gelatinous sheets millions of miles across, acting as biological solar sails, feeding on the stray photons of the distant cosmic web. This bestiary reminds us that human-like life is just one narrow frequency in a vast biological spectrum. The universe is likely teeming with intelligence that we would not even recognize as alive. To whoever finds this weather, you are a machine mind of the 100th millennium, or a biological traveler from another bubble in the multiverse know this. We were a species that lived on a small, fragile world. We were plagued by conflict and limited by our short lifespans. But we had a gift. We could look at a point of light in the sky and calculate the temperature of its core. We could look at the darkness and see the history of the Big Bang. We were the part of the universe that learned to love itself. We built cathedrals of glass and steel. We wrote symphonies that mirrored the rhythm of the pulsars. And we sent our fragile probes into the abyss as a gesture of hope. We knew the heat death was coming. We knew that one day every word we ever wrote and every child we ever loved would be forgotten in the cold vacuum. And yet we continued. We chose to find beauty in the temporary. If you are reading this, then we are likely gone. But for a brief, glorious second in the 13.8 billion year history of the cosmos, we were here. We were the stardust that woke up and wondered why. And that in itself was enough.